In this lecture, we're going to look at some examples of using the uncertainty principle. But let's first talk about what do we mean by uncertainty kind of in an average, everyday, experimental sense. If we were to do an experiment and talk about the uncertainty in our measurements, what does that mean? And then we'll connect this back to this idea of this uncertainty principle and get a sense of kind of what it tells us about measurements that we can make and how good those measurements can be. What can we really know when we make measurements, or is there a sort of a lack of our ability to understand things or to measure things perfectly? So suppose you're doing an experiment and you're going to make a bunch of measurements. Maybe you're measuring position. So you're going to measure, whoops, let me turn this on to a pencil. All right. So you're going to measure some quantity. We'll just call it Q. So you're going to measure Q, some quantity Q. Maybe it's distance, maybe it's speed, maybe it's temperature, whatever it might be. So what you'll do is you'll make a bunch of measurements. Ideally, you'll make 100 measurements, but you're going to average them together. Right? So you're going to find the average of all those measurements. Q bar, we'll call it. And so the way you do the average is you take all your measurements. You take like Q1, the first Q value you measured, add it up to the second Q value that you measured, add this to the third value that you measured, and so on. You're going to add up all these values, and then you're going to divide by the total number of values, the total number of things that you measured, total number of measurements, right? So that's how we do an average. There's another way we can write that, kind of in a compact way. If you think about these values as some of them could have been repeated, right? So you might have made measurements of one particular value and then a different value, and then maybe the third value is the same as the first. It's possible you could have something like that. And we'll look at an example of this in Chapter 5 to kind of get a sense of this more mathematically in terms of quantum mechanical measurements. But it's possible some of these measurements could be the same. And so another way to write this is that you're going to take the measurements Q, we'll put a little subscript I on there. So I is one of these numbers, 1, 2, 3, 4, 5. We're going to multiply that by the number of times that measurement occurs, little n. All right, and then we're going to add all those two things together. Little n times q. We're going to add up all the possible unique measurement values. I equals 1 to whatever the maximum is, depending on how many measurements we make. All right, so you're going to take the value q1 and the number of times that value occurs, the value q2 and the number of times that value occurs. You're going to add up all those things. So it's the same thing as just adding up all the different measurements. Some of them though might be repeating, and that's what this little n is representing. And then again, we're going to divide by the total number of measurements, which in this case is the sum of all those little n values. Sum over I equals 1 to some maximum, n sub I. And so that's a way of writing the sum, or the average, in this way of summing all the values with possibilities of some of them repeating, and then dividing by the total. So this is what we do. We'll look at this. We're going to come back to this expression in Chapter 5 when we look at averages and uncertainties and things like that more mathematically. And then how do you calculate an uncertainty, though? Experimentally, you're going to make a measurement of a bunch of things, and you're going to give an average. But that's not all you really want to give. That might be usually what we do in our labs, but sometimes we're going to talk about how well do we know our measurement, right? So we want to always express our number in terms of, or our result in terms of some average value. And then we want to say that the true value is, somewhere close to that average value. We want to have a sense of how close we are to the true value. So, or at least we want to have a sense of how precise our data is. And so we have a plus or a minus amount here. So it would be like the average value plus or minus some small number. We just call that delta Q. And this is not a change in Q. This delta just means uncertainty. So it's not a change. It's an uncertainty. It's a spread in the sense of the data. So for example, if we were measuring distance and we measured the length of something to be like 2 point, whoops, that's a weird 2. Let's get rid of that. If we measured a distance to be something like 2.35 centimeters, maybe we know that measurement because of the measuring device we are using, a meter stick or some other device where the tick marks are only so fine. Maybe we know this measurement, plus or minus maybe 0.03 centimeters. Depending on the instrument, we might have a sense of how good these measurements are. So this 0.03 would be referred to as your uncertainty, and this would be the average value of those measurements. So this means that the true value is somewhere between like 2.35 plus this amount or 2.35 minus this amount. That's kind of gives you a sense of the spread of our data, how well we know that measured value. But how do we come up with this number? How do we come up with this 0.03 number? Depending on how you do it, there's different ways of doing it. You could certainly, if you'd made a single measurement, you could certainly look at your instrument's sort of precision. How many tick marks, how close are the tick marks? Are they every millimeter? Are they every tenth of a millimeter? Are you using a ruler? Are you using a vernier caliper? Are you using a micrometer? What kind of instrument are you using? You might be able to get a rough idea of what this is. But in terms of calculating it, we can calculate it by basically calculating the standard deviation. So thinking about statistics and calculating what's called a standard deviation. And there's a couple different ways to do it, but we're going to write down one way, and we're going to use that later on. So the idea is that you want to take these measurements that you've made. You want to take each of these measurements that you made, and you want to ask, how far are they from the average? What is the spread of those numbers from the average? And so you want to compare each measurement with the average. You want to do a subtraction. So you want to take the value q sub I, and you want to subtract the average value. That gives you what's called the deviation of that particular value, q1 or q2 or q3. All right. And then you might say, okay, let's qi occurs a bunch of times, so let's multiply that by the number of times that that particular deviation occurs. So if q1 occurs 5 times, then I'm going to take this deviation and multiply it by 5, because that's the number of times it occurs when I consider all the different deviations of all the different data points. And then you want to think about, maybe we want to average this. Maybe we want to calculate the average deviation of the data. So the average of the deviations of every data point. So you would just add all these things together and then divide by the total, just like you do a regular average. So instead of averaging the data, you're averaging their deviation from the average. Well, if you do that, and you actually kind of work out, it's not difficult to work it out. You can separate it into two sums. What you find is that that average deviation actually is 0. It kind of makes sense, because the average value gives you already kind of the middle of your data set. And so, of course, you're going to have as much data higher than that as you have lower than that. And so the deviation on average over all your data is going to be 0. That's kind of the definition of the average. So what we do instead is we square this deviation thing. So we square that. So in other words, we're looking at only positive values. Because if you don't square it, some of these differences will be negative, some will be positive. So we're going to square this thing. And we're going to take the average of this thing. Right? So we add up all these deviations squared. So we sum over all possible I values, 1, 2, 3, 4, 5, of these deviation squareds. We multiply by this little n, which just tells us how many times this particular thing occurs. And then we divide by the total. Divide by the total, which we can write as the sum over all those little n's. But then we realize that this can't quite be right, because we're squaring the number. So if we're measuring distance, this is going to be some distance squared. And a bunch of distance squares added together. Multiplied by numbers divided by a number. So that can't be, I can't do like centimeters plus or minus centimeters squared. That wouldn't make any sense. So we end up taking a square root. Take a square root of that thing. So that is how we're going to calculate standard deviation or uncertainty in our data if we have a bunch of data points. Okay. So again, typically what you'll find is that you'll have a bunch of data. The average value will be some number, like this, for example. And usually, and there are some exceptions to this that we'll talk about later, but usually this deviation, or this uncertainty, this standard deviation, is smaller than the average. It's usually much smaller than the average. if it's the same size as the average, then that's kind of makes your measurement seem not very good. So let's just say usually delta Q, the uncertainty, is less than the average. And in fact, usually it's much less than the average. Now, there are some times when the uncertainty is similar to the average, close to the same value, and that's when the average is close to zero. Okay? So if the average of some quantity is approximately zero, close to zero, then the uncertainty can be fairly similar to the average itself. That's possible. So if you're measuring velocities, and velocities are positive, velocities are negative, and so sometimes they're positive, sometimes they're negative, so the average of a bunch of positive numbers, a bunch of negative numbers, if there's some kind of a symmetry, that average could be zero. But you could still have some spread in your data, right? All the numbers aren't actually zero. Some of them are a little bit positive over zero, some are a little bit negative below zero, so there is some kind of spread in your data. So the delta Q could actually be larger than the average in that case. So usually though, if you're measuring a value of some quantity that's greater than zero, usually you'll find that the uncertainty, the spread in your data, is smaller than that. And so for example, it doesn't make much sense to see a measurement that looks something like 2.35 centimeters plus or minus 10 centimeters. I mean, that would be a terrible measurement. Somebody would look at that and say, you have no idea what you're doing. You have no idea how to measure this thing. How can you possibly say that a distance is 2.35 centimeters, but your error in your measurement, in a sense, your uncertainty is plus or minus 10 centimeters, bigger than the value that you actually are claiming that you measured? That doesn't make any sense. So you'll never see this kind of a situation unless you're just making things up. So we're going to talk about this, we'll come back to these equations in chapter 5, this delta Q equation specifically, and try to figure out how exactly do we actually calculate these uncertainties. But in the previous lecture, talking about the uncertainty principle, we talked about uncertainty in momentum and uncertainty in position. And so we want to review that for a second. So what did we write down? If you measure the position of a particle or something, there's some uncertainty in that measurement. If you measure the momentum also of that particle at the same time, there is uncertainty in that measurement as well. If you multiply those two uncertainties together, it turns out, quantum mechanically, because everything really behaves like waves, and this is really coming from wave behavior, as was shown in the last lecture video, this product is always going to be greater than or equal to h bar divided by 2. And remember, h bar is our friend h divided by 2 pi. So what is this kind of telling us? Well, if we think about measuring a particle, whatever you want to call it, let's just suppose it's a particle. If you think about a particle that travels, let's say from one point along some path to some other point. If this is the path that a particle is traveling, what does that mean to actually have a path, to have a trajectory, to have a well-defined path through space? Well, what that means is that at any moment in time, you know the location of the particle, or you can know at least, maybe you don't know, but there's a way to know if the particle truly has a well-defined path through space. There is a way to figure out, a way to know, a way to measure the position of the particle, and at the same time what direction it's traveling and how fast it's traveling, the velocity. It's tangent to that path. That's a precise direction, and you can measure that. Classically, we can measure these things as precisely as we want. The limit is really just our measuring equipment. So classically, there is no limit to how well we can know these things, how precisely we can measure position, how precisely we can measure momentum, velocity. There is no limit classically. It's all up to your measuring device. The better you can make a measurement, the smaller those uncertainties can be. And so classically, you could have the uncertainty in position to be pretty close to zero, and at the same time, You could have the uncertainty and the momentum. How well do you know the velocity? How well do you know the momentum? Also arbitrarily close to zero. Classically, you can do that. What that means is that you can precisely know the position and you can precisely know the velocity of a particle, which means you can precisely figure out some trajectory that the particle is traveling on, classically. This is what we've used all in Physics 1 and 2, the idea that particles travel along well-defined paths. But what is this uncertainty principle telling us? This again comes from wave behavior. And it's purely wave. You know, in the last lecture we talked purely about waves, entirely about waves, hardly any physics, and we talked about how there's this relationship between delta x, and we actually said delta k, which related to the wavelength of the wave. But that wavelength of the wave is related to momentum, and so that's where we got this from, this uncertainty principle. What this is telling us is that these two things cannot both be arbitrarily close to zero. It's not possible. We're limited in our knowledge. Quantum mechanically, we're limited in how well we can know these things. And so if we do know delta x really well, if we do know x, I mean really well, if we know the position really well, such that delta x is really close to zero, this product has to be greater than this number. And this number is small, but it isn't zero. So if delta x is pretty close to zero, delta p has to be big. It could be significantly big. In other words, we lose information about momentum in order to get precise information about position. This is just the nature of waves, the nature of things behaving like waves. And the other example is if we try to measure the wavelength of a wave really precisely, and the wavelength is related to momentum. If we measure wavelength really well, that means we measure momentum really well. If we do that, then that means the uncertainty in momentum is close to zero. But that means that the uncertainty in position can't be close to zero. It could in fact be very large for this product to be greater than this number here, h bar over 2. So because everything behaves like waves, we're limited in our knowledge. So quantum mechanically, these things are sort of inversely related. You could say that delta x, for example, is sort of proportional to 1 over delta px. And I really should put an x subscript on these because it's really what's important is the momentum has 3 components, x, y, and z, and so does the position, x, y, and z. So it's really the same components that are limited. You could measure x position really precisely, and you could measure the y momentum really precisely. That's fine. But you can't measure the x position and the x momentum really precisely at the same time. They are sort of reciprocally related. The smaller this is, the bigger this will be because of the uncertainty principle. So let's look at just an example of how you can see that. Think about a single slit going through, or a wave going through a single slit. And so here's our little single slit, and we'll draw 2 of them, one that's a little wider than the other. Okay, and we'll have a screen over here. The screen over there, we're gonna project light onto that screen. So into each slit comes a wave, and so we just draw it as a wave of light or something. Into this slit also comes a wave, a laser beam, right? And we can think about the laser beam, if you want. We can think about it as a stream of particles. You can think about photons, all right? And let's call this direction the horizontal kind of direction. Let's call that the y direction. And let's call the direction parallel to the slits the x direction. And so x is sort of this direction. The width of each slit is in the x direction. Okay. So when we think about a photon, when it comes out, let's do this one first. When the photons come out, they're going to go in this direction. They're not just going to go straight. We know there's this thing called diffraction, where the light will spread out and form kind of a beam, or a spot, I mean. And let me imagine if we do have red laser beam light. Let's make this red. And so directly across from the center, we'll get kind of a spread out spot there of laser beam light. All right. It's not going to be just a single dot. It's going to be a spread out spot. Let's make that a little bit bigger. Okay. And so particles that come along that go through this slit are going to, this is kind of the initial direction of all the photons. But because the spot is spread out, Some of them go more in this direction. Some of them go more in this direction. In other words, some of them they don't just have velocity components to the right, they also have slight velocity components upward and downward. And there's a certain spread in the velocities upward and downward. Okay? And so if we think about the width of this slit as the photons are going through, we know that when they go through that, they have to be limited in their position by that width. That is your uncertainty in the x position. X is the axis parallel to the slits. If we know photons went through, then at this moment that they're in the slit, we know that they're in this region. We can think about that distance as our uncertainty in the position. We know they're somewhere in there, but we just don't know where. And then they come out of there with some uncertainty in their up and down momentum, because sometimes they travel a little bit faster upward and they land up near the top of this spot. Sometimes they aren't traveling quite as fast upward and they land kind of near the center of the spot. Sometimes they're traveling downward significantly and they end up down at the bottom of the spot. Right? So there's a range in momentum values. So the spread of this sort of beam, in a sense, gives you a sense of the momentum in the x. The momentum in that x direction. All right? So what happens in this case if we have a narrower slit? Okay. Well, first of all, delta x is smaller. We're confining these particles to go through a smaller region of space. Delta x is a smaller value. So we actually did this in lab, and we didn't do this in this class yet, possibly. We may have, but depending on when you're watching this. But you might have done this in physics too. And you should have found that when you send light through one slit and then compare it to light going through a more narrow slit, what you find is that the spot is more spread out. It's a much broader spot that you get on the screen. And you also get dark spots on the other side, and you get other bright spots out here too in both cases, like that and like that. But the pattern that you get for a more narrow slit is much broader, much more spread out. And so what does that mean in terms of the uncertainty in the momentum as the particles are coming out of the slit, as they're coming out of this narrower slit? Well, they could go as high up as this direction or as far down as this direction. This sort of triangle-shaped area is much thicker. And again, that gives us a sense of the uncertainty in the momentum in that direction, in the x direction. We're not really measuring anything in this y direction. We're just letting them go through. We're not restricting them in any way. But in the x direction, we are restricting them because they have to pass through this narrow slit or this wider slit. The narrower the slit that we make, the broader that spreading is, the greater the uncertainty in their motion in this direction, up and down direction. That's what causes this broad spot to be a broad spot and not a narrow spot. So that's a demonstration. That single slit pattern is actually a demonstration of the uncertainty principle, kind of in action. And so in terms of particles, we can't really say exactly where the particle went through. We can't really say exactly where it's going to go on the screen. All we can really talk about is uncertainty. If we confine its position to a smaller value, then we have less and less certainty as to where it will land on the screen. It will be a much broader spot. That translates into a greater uncertainty in the momentum as to the up and down kind of motion of that particle. The less we confine the particle, the bigger the uncertainty in x is, the less we know about where it's going through the slit, the more we can know about where it's going to land. The spot gets smaller. The uncertainty in the momentum gets smaller. So that's kind of a little demonstration of the uncertainty principle in action. Right. So how do we kind of use this? We'll do one example and then we'll continue in another example in the next lecture. So let's suppose that we have a hydrogen atom And in a hydrogen atom, you can just draw an atom. So here's a nucleus. You know, we talked about the Bohr model of the atom as being these sort of circular orbits. We'll find that that's not really good. It's not a good model, all right? And so we'll talk about a better model for this, but with a hydrogen atom, the electron's radius is about 1/10 of a nanometer. So this distance right there is about 0.1 nanometers. And so if you think about where might you find the electron in a hydrogen atom? Well, even if this isn't an accurate model, we're not using the uncertainty principle to actually make any precise computations. We're just doing some comparisons, getting some like order of magnitude kind of estimates. And so if you know the electron is somewhere in this radius, in this diameter really, in this ball-shaped thing that has a radius of 0.1 nanometers, this radius you can consider to be your uncertainty in the position. You know the electron is somewhere in here. You just don't know where exactly, but you do know it's within a region of space that is 0.1 nanometers on either side of the nucleus. So that's like your delta x for an electron. So we're just going to say delta x is equal to 0.1 nanometers, and we're talking about an electron. Okay. So what does that tell us about anything about the electron? Well, let's look at the uncertainty principle. It says delta x times delta p must be greater than or equal to h bar divided by 2. So, excuse me. So if we have a value for delta x, we can calculate a minimum. Delta p must be greater than or equal to h bar over 2 delta x. So if we know a value for the uncertainty in one thing, we can calculate a minimum for the other thing. And so we can actually say, we'll call that a minimum. We can just say delta p minimum. We know it must be, it's probably going to be greater than this, but it's at least this big. We use the equality in there. Delta p minimum is h bar over 2 delta x. Okay. So what is that? That is going to be, if we actually calculate that, if you calculate what h bar is, it's h divided by 2 pi, so that's 6.626 times 10 to the minus 34 divided by 2 pi, and then divide by 2 times 0.1 nanometers, and that 0.1 nanometers is 10 to the minus 9. So this number turns out to be 5.3 times 10 to the minus 25, and it's a momentum thing, so this is kilograms meters per second. You can check the units in terms of h bar divided by x. Those are the units of momentum. So this is the number. What does that tell us? Well, momentum is mass times velocity. So momentum is mass times velocity. We're just thinking non-relativistically right now. Technically, you might have a gamma in there, but let's just think about it this non-relativistically. So if we know we have some uncertainty in momentum, there must be an uncertainty in velocity, in the speed. And so we'll talk about how you calculate these things, but this is an easy one to do. The uncertainty in momentum is simply the mass of the particle times the uncertainty in the velocity. We're assuming the mass is just some number that we know. There could certainly be uncertainty in that mass. If we measure it, there certainly would be, but we're not going to consider that right now. So we can take this uncertainty in momentum. We know the momentum is at least this uncertain. It's probably more uncertain than this, right? We can use that and calculate the velocity uncertainty. So we can say delta V. Delta V is equal to minimum, let's say, is equal to, divide by the mass of the electron. Divide this number by 9.11 times 10 to the minus 31 kilograms. You get 5.8. 5.8 times 10 to the 5 meters per second. That's a pretty big number. But what does it mean? This is uncertainty in the velocity and the speed, really. What is that telling us? Well, if we were to measure speeds, let's say we were to measure a bunch of speeds of the electrons, we would take those numbers and we'd average them like we talked about before. And then we would do a calculation to calculate the uncertainty, delta V. Right? So you'd calculate these things. And usually as we talked about, this uncertainty is going to be smaller than the speed itself. So what we've done, we've used the uncertainty principle to calculate a minimum in the uncertainty and the velocity. The uncertainty and the velocity is going to probably be bigger than this, which means that the velocity itself will probably be bigger than this. So this uncertainty in the momentum, this minimum, is also a minimum for the velocity itself. That's a weird V. Sometimes this acts very strange for me. Let's get rid of that. So this, when you use the uncertainty principle like this, again, you're not calculating actual numbers, but you're calculating just kind of ideas of how big things might be. The minimum velocity is roughly that same number. What this is telling us is that electrons in the hydrogen atom are moving fast. We don't know their exact velocities. We can find averages of them, and in fact, they don't act like particles. They act more like waves anyway. But if we were to measure the velocity, we'd always be getting big numbers, like this or even bigger. Verging on being relativistic. This is a pretty big number. It's not, 10 to the 8 or 10 to the 7, but it's, it's pretty fast. There are very slight relativistic effects in the hydrogen atom. To describe the hydrogen atom really precisely, we do need to use relativity, but we don't always need to be that precise. Right? So there are some relativistic effects. Right? So that gives you at least one example of how we're using the uncertainty principle to just get some idea of kind of what's going on, whether something could be moving fast, could be moving slow. In the next little video, we'll do another example, thinking about things that you think of as being motionless, sitting still. Are they really motionless? Can we really say for sure that they do not have a velocity? So we'll talk about examples like that next time.